Welcome to the world of microelectronics. It's a world of miniatures, where a high-powered computer like this can be the size of a dime. Since the invention of the transistor in 1947 at AT&T Bell Laboratories, scientists have made spectacular progress in designing ever smaller and faster electronic circuits. This microchip can process data just as well as a room-sized computer of 15 years ago. This AT&T memory chip contains about 600,000 working parts. It can store 10 single-space pages of typewritten text or data. These smaller, faster chips cost less to produce and operate more reliably than earlier microchips. Today, microprocessors perform functions that just a few years ago required piano-sized computers. Designing these advanced microchips can be a mammoth undertaking involving teams of engineers.
Powerful computer systems are used as simulators to test the structure and function of circuits. Simulations also help engineers determine how fast each particular circuit will work. By working with these computer models, the engineers can alter circuit designs to obtain maximum performance. Line diagrams are developed to show all the transistors and internal connectors in each section of the chip. And these diagrams are converted into symbolic drawings, which transfer all the information into another computer in the form of ones and zeros. Then, a computer stitches together the individual circuits developed by separate engineering teams. Before manufacture, the engineers often examine the complex drawings to be sure there are no design errors.
A short explanation makes it seem simple. It's not. It takes scores of scientists, engineers, and support people, each putting in 1 to 2 years of tough, painstaking work to make sure that a new chip meets all performance requirements.
Making a microchip starts with a thin wafer of silicon. Each wafer will become as many as 100 microchips. Because the tiniest particle of dirt can ruin a microchip, all manufacturing takes place in dust-free clean rooms. The wafers go through many steps to prepare them for the printing of the circuits. The circuit patterns are put onto wafers in much the same way that painters use stencils. The specialized stencils, called masks, are made of ultra-pure glass. Electron beams are used to expose the photosensitive surface and chromium layer which have been applied to the glass disc. To print the circuit pattern on the wafer, a light source is directed through the mask, exposing the light-sensitive material on the wafer. The result? Circuits for about 50 chips are etched onto this wafer. Each electronic pathway may be as narrow as 1/10,000th of an inch. The circuits then undergo rigorous tests. Each circuit in each chip must work perfectly. Finally, individual chips that pass quality control are placed into housings, and fine gold wires connect the chip circuits to other parts of the electronic equipment.
The finished product, smaller than my fingernail, can perform complex functions that make new services possible, like the popular touch-o-matic telephone, which can dial stored numbers at the touch of one button.
This is an advanced microprocessor designed and manufactured by AT&T. A view through a microscope reveals its awesome complexity. It has 150,000 transistors, over 300,000 internal connections, nearly 600 inches of interconnecting wires. The chip is divided into sections. Each section performs specialized functions. To get a closer look at the sections, just touch the appropriate part of the screen. The main controller is the commander-in-chief. It commands other controller sections to perform their functions and handles information flow. If two sections need to use the same part of the chip at the same time, the main controller makes a decision and solves the dispute. The instruction queue is like a waiting room. It's the area where instructions are held until an operating section is ready to use them. The registers are storage bins. They're where the chip stores data that is being processed. The arithmetic logic unit, ALU for short, is the calculator section. It performs the arithmetic. The address arithmetic unit, AAU for short, is responsible for performing various arithmetic operations to specify addresses, the locations for data the machine is to process. The I/O frame is the link to other components in the computer, like the memory storage unit or disk drive controller. Traditionally, information has been stored on paper. Now, data is often saved electronically and retrieved on a video screen. Computers store and retrieve data internally on microchips. On this tiny AT&T chip are 256,000 memory cells. Rows and columns of cells can be seen under a high-powered microscope. Each memory cell can hold an electrical charge. The presence of an electrical charge represents a 1. The absence of a charge means a 0. A set of 8 ones and zeros together signifies one letter of the alphabet. For example, this set of 8 bits represents the letter H. To retrieve information, the computer senses where ones and zeros are stored and transmits signals to the memory cells requesting the information.
This first random access memory was made in the early 1970s and stored about 1,000 bits of memory. Storage capacity has nearly doubled every year since. Now, the AT&T 256K chip is at the leading edge. It is smaller per bit, faster, and uses less power than any previous memory. Today, it is one of the most economical ways to store data in computer systems that require high-speed, high-capacity memory. From the tiny chips used in digital wristwatches and calculators, to the powerful chips used in business and personal computers, microprocessors seem to be everywhere. In fact, there are more microprocessors than people. On average, a family of 4 in the United States has over 30 microprocessors. Almost everyone also uses other equipment that relies on microprocessor controls. Office copiers and postage machines contain microprocessor and memory chips. New memory typewriters are based on microprocessor technology. And of course, so are microcomputers and mini-computers like those manufactured and sold by AT&T. In healthcare, microprocessors have become essential to accurate diagnosis and effective treatment of many illnesses. AT&T, with its many discoveries, inventions, and developments, has been a major factor in shaping this technology and will continue to be a world leader in microelectronics.
A suburb of Boston is connected almost instantly to a mobile phone in Chicago, and microchips control much of the process. Microchips in touch-o-matic phones store many phone numbers and dial those stored numbers at the touch of one button. Some touch-o-matic phones have microprocessor-controlled displays. When the call leaves the house, microchips in neighborhood equipment route the call to central switching offices. Here, microprocessors help select which of the many long-distance routes the call takes across the country. Microprocessors in switching offices throughout the country also monitor and measure the signal. If signal quality falls, microelectronic circuits automatically switch the calls to different lines. Once the call arrives at base stations in Chicago, it must be relayed to the mobile phone. Microprocessors in the mobile phone detect the signals from 2 base stations simultaneously and select the stronger signal, assuring quality reception wherever the car goes. Finally, microprocessors collect billing information, including the number called, the length of call, and class of service. This data is relayed to the central billing computers for processing. Because of microchips, long-distance telephone service is more convenient, reliable, and economical today than ever before.